Alright, so this is going to be a video on taking the derivative of arcsecant of x. And the first thing I point out is in the top left that if arcsecant of x equals y, then the secant of y equals x. That's just because if I take the secant of both sides here, right, if I say secant and I make this inside, these inverses will cancel and I'll just be left with this x right here. And on the other side, of course, it'll just be secant of y. And I just flip that around just for simplicity, but that's it. And then, of course, we start this off with implicit differentiation like we have with the past three. I suggest you watch those first before you watch these to kind of get the hang of the process, because the processes themselves are pretty much the same, just a little bit of tinkering with the Pythagorean identity, and that's just about it. But we're just going to start with implicit differentiation here, and I'm going to take the derivative of both sides, secant of y equals x. So I'm just going to write the operator d over dx right here, and I'm going to have secant of y equals d over dx of x. And then I can expand this. The derivative of secant is tangent of y times secant of y. And then, of course, we're going to have dy over dx using the chain rule. And then I'm going to say this is equal to, the derivative of x is just 1. I want to isolate dy over dx, so I'm going to divide both sides here by tangent of y times secant of y. So I'll just be left with dy over dx on the left-hand side equals 1 over tangent of y times secant of y. Okay, and then if you look back up here, secant of y equals x. So really, if I want to, I can just write this as tangent of y times x. So I'm going to do that down here. I'm going to write dy over dx equals 1 over x times tangent of y. All right, and then I want to solve for tangent of y, and I want to get this all in terms of x. So I'm going to look back over here at our Pythagorean identity, sine squared of y plus cosine squared of y equals 1, and I'm going to divide everything here by cosine squared. And what that will give me is tangent squared of y plus 1, cosine squared over cosine squared is 1, and then 1 over cosine squared is secant squared. And then I'm going to want to isolate this tangent squared, so I'm going to subtract 1 from both sides, and I get tangent squared of y equals secant squared of y minus 1, and then I'm going to take the square root of both sides to get just tangent of y alone, and that will equal the square root of secant squared secant squared of y minus 1. Okay, so I can substitute that in for tangent of y here. But before I do that, secant squared of y, up here we know secant of y is equal to x. So secant of y times secant of y is secant squared of y. So I can just say x times x, right? So this would be the square root of x squared minus 1. So I'm going to redo that over here. Dy over dx equals 1 over the x that we had earlier times the square root of x squared minus 1. Okay, and that's our derivative, but there is one more step that we have to do. And you kind of have to observe the graph of arcsecant of x itself here. So if you look down at this graph I pasted in the bottom left corner from Desmos, I just graphed arcsecant of x, and you'll notice the derivative, or well, the slope or the gradient of this graph is actually never negative. But using this formula we've developed over here, we could get a negative slope. And we know that's not true. If I were to plug in something like -4, we would get 1 over negative 4 times the square root of 15. And that will be a negative slope. Whatever that slope is, I'm not going to evaluate it. But just know you could get negative numbers by putting in a negative x, as long as it's not like this between these right here. Of course, that'd just be undefined. But that's an issue, right? We can't have a negative slope. That would not be true, because we know, just looking at this, that the slope is never actually negative. So the way that people have come around and fixed this is they said, okay, let's just do the absolute value of x. And that seems to work out pretty well. This absolute value of x rules out any possibility for a negative to influence this derivative, because this is the only place where a negative would be able to be plugged in, because x squared, the squared exponent will automatically make it not negative, of course, and then the square root itself, you can't have a negative, you can't take the square root of a negative number, so it's not like that would change anything either. So that was the root of this problem here. So if you take the absolute value of x instead, you'll notice that this will work for all instances, because if I take the derivative here, it's positive. If I take it here, it's positive. It's never actually going to be negative, which is why that was an issue. Even if you go all the way out to infinity on either side, you will never find it to be a negative slope. And so by installing this absolute value sign, you fix it. And that is the complete derivative of arcsecant of x.